So we're wrapping up our discussion on using Kalman filter type methods to estimate the health of a battery cell, although you'll notice that there's still a pretty hefty portion of this chapter remaining because we do have an alternate approach to estimating capacity that has some big advantages over what we've seen so far. But before we leave this section on EKF or SPKF for capacity and resistance estimation, I need to talk a little bit about robustness of the method and speed or computational complexity of the method, because these are really important when we're implementing something in a small processor. In an embedded application where we don't have a lot of supervisory control over what's actually happening and not. So robustness is a concern. Can I guarantee that the method is going to converge to something, some meaningful estimate? When I run a Kalman filter to adapt the state, and my filter is correctly implemented and all that, it will converge to the neighborhood of the state. That will work fine. If I write a method to estimate the parameters given a known state, that will work just fine. But when I try to estimate both of them together using either dual or joint filtering, there can be a big problem. And this is the reason. I've got input to the system. Inside of the system I've got some state, but now I also have some theta. And I've got output from the system, so I've got current in and voltage out. I measure that, and I run my filter. Now my filter is trying to adjust the x hat and the theta hat so that the relationship between I and V matches closely. And it can do this by adapting either the state or the parameters or both. Now, in the previous chapter, when we estimated the state only and assumed that the parameters were fixed, that helped the Kalman filter realize that, oh, I need to adapt the states because the parameters I know. Or if I knew the states and was estimating the parameters instead, the Kalman filter would leave the states alone as it was supposed to do. But here, because it has the flexibility of adapting both, it may try to overfit the current voltage data, and in doing so, in other words, try to fit the noise or try to account for errors in the model equations or inaccuracies in the model equations themselves by adjusting the state and the parameters in such a way that makes the current to voltage behavior appear to look good, but loses all physical meaning whatsoever in what the state means and what the parameters mean by themselves. And one thing, especially if you put high covariance on some things that really shouldn't have high covariance, you could adjust something, the voltage of this cell equals OCV plus hysteresis minus your diffusion voltages and then minus K times R0. One thing I've observed these filters do is, because that is such a large component in the voltage, is that they don't change anything except R0. And it says, oh, if I adjust R0, I can make any voltage I want. Now it's adjusting R0, so R0 versus time looks like this. Why is it doing that? Well, because the covariance placed on the sigma R component driving R0 is too large. You're allowing too much variation in that resistance. And the Kalman filter says, well, you let me do it, so I'm going to do it. I'm going to change the easiest thing for me to change to make the voltage behave in a way that I want it to behave. And when you do that and you adjust R0 so rapidly, it's adjusting the other parameters and states as well, but it may be doing so in a completely bizarre way, such that you're just going to get meaningless, truly meaningless results. So there's no built-in guarantee when you're using a joint or a dual filter that the state of the model converges to anything with physical meaning, and that is a big problem because we're relying on state of charge being state of charge and hysteresis being hysteresis and so forth. So we are concerned about this. We want a very specific meaning. So does this mean that we completely disqualify this method? Absolutely not. We just have to be very careful. One thing to do would be to adjust the covariance matrices sigma r so that you have very slow adaptation, and that can help. It doesn't prevent, but it certainly helps the situation. And another thing is, right now we've been assuming the input to the model is current and the output is voltage because that's really what we measure. But if we could somehow fabricate additional outputs that I measure or compute from measurements that maybe are approximately equal to a state or approximately equal to a parameter, these fabricated outputs could be extremely noisy, but if they have no offset, no bias, I can use them to keep the estimates of the state and parameters honest, in the sense that they won't drift away from the mean value. They may be noisy, but they won't drift away from the expected value, and that helps keep the filter on track. So let's do this with one state. State of charge is pretty important for our application. I measure current, I measure voltage, I don't measure state of charge, but I can fabricate an approximate measurement of state of charge that's really noisy, but it's pretty much unbiased too, and we're going to use that to help keep our filter honest. So suppose we model our cell terminal voltage as voltage is about equal to OCV minus IR. Yes, we're getting rid of a lot of effects that we know about, but this is just a very simple model with very few inputs. I want something simple and crude here. I solve for OCV. OCV equals V plus IR, and I do the inverse of OCV function on both sides to say that a noisy estimate of state of charge is equal to the inverse open circuit voltage function evaluated at the voltage Vk plus IR. You've done this, I think, on a homework assignment already. If you haven't, you will. And this was called the Tino-based state of charge estimator. And we saw when we used it as a state of charge estimator, it was pretty terrible. Of course, nobody uses this in a real vehicle. But when we look at it from the point of view of, can I create, using only measurements that I have and very little additional information, can I create some kind of even a noisy estimate of state of charge that would help me keep my filter honest to say, wow, this does have application here. And I think we've seen this figure before of a very dynamic test of current into this cell producing very dynamic voltages, and in this plot the dark green line is the true SOC and the blue line is the SOC estimate using this equation. And we concluded that the SOC estimate was pretty awful, but if you look at it, you say, is it biased? Hard to tell from this plot. There are certainly larger excursions in the upward direction than the downward direction, but I think we're actually spending more time in the downward direction. So I think there's very little bias, constant offset in the Z hat measurement that's produced using the Tino method. So suppose I know R0 somehow. Maybe I can use my simple R0 estimator that we saw before. That should work fairly well to get a decent estimate of R0. And suppose we know the inverse OCV function, which we should know for our cell, and it doesn't change very much as the cell ages. Then we can definitely compute this. Just a table lookup. How do we use this? Well, in our models so far, the Kalman filter has output equation that we've so far said is just voltage, but we can use vectors. So for our output equation, now we're going to compute voltage as one component only that we do measure, but the other component of our output equation is the true state of charge, Zk, of our model. We're pretending, if you will, that we can measure Zk as well as measure voltage. Well, we then run the dual joint Kalman filter using this modified two-output model, and the measured information is the actual measured voltage, including noise and so forth on it. But then we fabricate this SOC estimate to go along with the assumed measurement of SOC. We acknowledge that this is really noisy, but we can get an idea of the uncertainty of the estimate by measuring the variance of this noise in a lab test. So we can have some idea of that. And now we have a two-output system where it appears to the Kalman filter like we're making two measurements. We're not. We're making one and fabricating the other measurement, but we operate the Kalman filter this way. And what this does is it makes a very strong coupling between Y and X, especially inside of X. It makes a strong coupling with the state of charge state, and it keeps that state honest. And if we could fabricate other estimates of the other states, it would help keep those states honest as well. So we acknowledge there's noise in Z hat, some short-term bias due to hysteresis and polarization voltages and so forth. We can't use this as a primary SOC estimator, but the expected long-term behavior is pretty much unbiased, and that helps us maintain the accuracy of our SOC state, and that is pretty important for us. So anytime you use a dual filter or a joint filter, I would say you must do this. If you don't do this, it will not work. What about computational complexity? If I have all of the states and all of the parameters being estimated, we have a fairly complicated algorithm, requires a lot of floating point operations. We may be able to get away without estimating everything. So suppose some cell model parameters we assume don't change very quickly, and we just leave them as constant, and we estimate only a couple of cell model parameters as they vary with age. Then we might consider some simplified methods. And so here we finish up this section with some ideas for simple estimates of resistance and capacity. So suppose we want to estimate resistance only. We could actually implement a very simple nonlinear Kalman filter to do this. What we do is we say that the resistance moves around with a fictitious noise, just like we've seen before, but notice this is a single state. This is not a large state vector or a large parameter vector. It's a single thing. So any computations we do with this are scalar computations, and they're fast. And then we need an output equation. So suppose we say voltage is OCV minus IR plus some noise. In other words, I'm ignoring hysteresis, I'm ignoring the diffusion voltages, and I have this crude output model, and would have to model a fairly large noise to account for the fact that the output equation is crude, which means that we'd have slow updates, but that's okay. The resistance doesn't change very quickly. And so we implement either an EKF or an SPKF with these equations, and that will give us a good estimate of resistance over time. This is very similar to what we did with the crude estimate of resistance at the beginning of this chapter, except now we are doing something a little bit more theoretically defined. We're using the same model, OCV minus IR, but we're using the Kalman filter to adjust the covariance matrices, and we actually have an uncertainty of the resistance using this method, whereas we didn't with the other method, and we don't have to choose some filtering constant alpha, because that's handled by the signal-to-noise ratio of, the ratio of these different terms here. We do need for this method an estimate of state of charge from some external source. So we assume probably that we have some kind of an EKF or SPKF running to give us a state estimate. Or I suppose I could try the Tino estimate here. I haven't tried it. I don't know how it would work. I think basically you're undoing. Yeah, I don't think that works because you basically your z hat equals OCV inverse of v plus IR, and that would end up unwrapping everything, so you get 0 equals E, which isn't true. So I don't think that works. So I don't think we can just use the Tino estimate here. I think we have to use something a little bit more precise than that. But in any case, this is going to give us probably a better estimate of resistance than we've seen so far, but with a very simple method with only a couple lines of code. We could consider trying to estimate capacity using the same kind of idea. Here again, I need a state equation for my parameter, and there it is. But I need an output equation, and we have a problem because if I look at voltage, it's equal to OCV plus hysteresis minus the diffusion voltages minus IR. Capacity is nowhere to be seen in that equation. It's only indirectly in here and very indirectly in there. So somehow I have to fabricate a measurement of that includes capacity in it to make any kind of a Kalman filter that's reasonable. One way that I've done this is to take two state of charge equations at adjacent time instants. Well, actually, no, sorry, it's one. We know zk equals zk minus 1 plus, minus eta k minus 1 I, k minus 1 delta t over q. If I bring everything over to one side of the equation, I get 0 equals zk minus 1 plus eta dot dot dot. I have this deterministic relationship. And I call that a fabricated measurement using estimates of state of charge at two adjacent time samples from some state of charge estimation system that we've implemented externally to this. So I make a desired measurement signal. Well, I compute a measured signal to be this. And of course, theoretically, it's 0, and in practice, it's not 0 because of SOC estimation errors and current estimation errors and so forth. So this EK is this fictitious measurement noise that models the error in the Z hats and the errors in the measurement of current. With this equation, then, I implement some kind of a nonlinear Kalman filter. I compute my D hat to be this, but then my known measurement is this, which is equal to 0, and then I use the difference between them to update the capacity estimate. In order for this to work well, these two things have to be very, very good, and that is kind of the crux of the problem with estimating capacity in general, is I need a very good SOC estimator to do it well. That concludes our talk of using Kalman filter type ideas to estimate resistance and capacity. Now we are going to look especially at the capacity estimation problem again, because we've kind of made some assumptions along the way without thinking about it that are suboptimal assumptions that lead to a bias in our capacity estimates. And for us to be able to correctly estimate capacity, we need to consider the math a bit more carefully. So the remainder of the chapter will be looking at capacity estimation using a different approach.